Hello everyone. We'll start our discussion or we'll continue with our discussions of problems in this lecture. Now as you can see here, I have already drawn the diagram. It is again a simply supported beam where the loading is in the form of a point force acting vertically downward at the midspan of the beam. So you understand that this entire length is L and this P is acting, this point force P is acting at a distance L by 2 from the left end. The cross section is also very familiar to us. The simplest of cross sections, the rectangular cross section having width B and height h. However, the big difference that this problem has is that the material behavior is not linear. So the material behavior here is given by sigma is equal to some coefficient k times epsilon to the power 1 by 3. Now you note that no subscripts are given here. That is because we are still adhering to the understanding that for this kind of a problem, the dominant the dominant stress rather will be still in the form of sigma xx, where we understand that x is in this direction. Okay, so maybe I can specify that more clearly, that this still is our x direction and this is indeed sigma xx. Now we could have a more general nonlinear behavior, the representation of that, but at least for our current purposes of illustrating a problem where Castigliano's theorem is used, we will take this kind of a simple nonlinear behavior and see what is the implication of it. You will find out in the course of this lecture that we'll have to go through certain involved things. Now towards that end, first of all, we note what are the things that are similar with our previous understanding. First, you note that all the things that are related to the statics aspect of this problem, meaning that how the reaction forces will be, as you can understand directly from a visual inspection of this problem and based on all your undergraduate experiences, the reaction forces here will be P by 2 at this end and P by 2 at this end, both acting vertically upward. That does not change, certainly. Furthermore, the connection that the strain has with the geometry, which we have developed, which we all know from our undergraduate studies on beams, that also does not change. What will change, however, is everything or every aspect associated with those formula which does involve this kind of a connection between sigma and epsilon. So first of all, you note that earlier we have talked about a simply supported beam problem where the material behavior was very much linear elastic, and there we had used this formula which we had developed earlier, that the deflection. Okay, so please note that for linear elastic behavior, if for linear materials, for linear material behavior, d is equal to like this, where u, mind you, is the strain energy, and we have already seen that this strain energy it can be represented for the case of a beam in this form, m squared by twice ei dx, going the entire span of the beam from length from 0 to L, and this can be further simplified to del m, sorry about that, okay. So we have been using this this formula. Furthermore, as a corollary to the Castigliano's theorem, we had also noticed that we could have a corresponding formula for the slope where we noted that theta is equal to del u del m, where m represents the bending moment. Okay, the point here is that this all these things is not going to be valid, okay, not valid here because of non-linear material behavior. This is the absolute fundamental thing that we have to understand. So what can we use? Okay, so towards that end, you first of all note that what is the expression for this m. Okay, we can start off with from scratch, basically from the understanding that the bending moment is basically a manifestation of the forces that are induced or connected with this sigma xx, and we directly use the geometry that we have for our problem here. So this b dy, it represents an element, a thin strip, an elemental strip here, and we take the integration from over the entire height of this cross section. Okay, this y here is the moment arm. All right, so you all know this, but let us see what is the implication of using this expression of sigma here. Okay, so if we use that, what we are going to obtain, let me quickly go through it. Now what? You see, as I had already mentioned, the connection that the strain has with the geometry, that does not change, even though the stress-strain relation has become non-linear. Okay, so the kinematics part, that is not changing. So if the kinematics part is not changing, what we note that epsilon, that we understand like this, is still very much given by this formula, that epsilon is equal to y by r, where this capital R, it represents the radius of curvature. Okay, it represents the radius of curvature. Many of you who have had a very strong gate preparation, things like or formula like this, mr is equal to ei, those kinds of things would be very much at your fingertips. And please note that the r that you have over there in that formula, it is that same r. Okay, it is the radius of curvature, but as we'll see, we have to specialize this, or we have to generalize this to the fact that this is the local radius of curvature. Okay, in any case, for our present purposes, we proceed with the application of this formula. For the students who may not have gone through a gate preparation, please note that this formula, it basically arises from the fundamental, well, I should not say fundamental, but the very elementary Euler-Bernoulli beam hypothesis. Okay, so if you are not if you don't recall it, I suggest that you go back to your undergraduate textbook, and you will find the discussion in the chapter on bending, or maybe even in the chapter on flexural stresses or bending stresses. Okay, so we have this 1/3 over here, like that. And now see, I can take this k out of this integration. I can also take this r to the power 1/3 out of this integration, because you note that this r could in general vary along the span of the beam, that is along the x direction. But here we are here we are carrying out this integration over a particular cross section. So at a particular cross section, we are at a certain given distance x from the origin. Okay, so there is no chance of r varying over the y, which is what this integration is with respect to. So we can take this uh, k out, we can take this b out, this r to the power 1 by 3 out, and what we are left inside is this integration minus h by 2 to h by 2 y. So this 1 by 3 and this 1 together, it gives me a 4 by 3. And this is where you will note that things start to become a little bit weird, but also certainly very interesting, and you get to see the direct implication of the nonlinear behavior. Okay, so proceeding with the algebra, what we'll obtain is this y to the power 7 by 3 divided by 7 by 3. I mean, the first time you do it, it all sounds a little bit, I mean, quite offbeat, but not to worry. And please note that we have the integration limits over here, h by 2 to minus h by 2. So that gives me h by 2 7 by 3 minus of minus h by 2 7 by 3. So overall, what this will give me, so I'll get a 2 twice of h by 2 to the power 7 by 3 over here, and together that is going to give me this 6ab, and 7 remains as it is, and there is this h by 2 to the power 7 by 3. Okay, so basically this gives me a twice, and that twice I have multiplied. Okay, so you see this m is this this weird looking, quite a complicated looking thing, but overall you please note that what is happening, what is really happening here. This 6, the constant, this k is another constant which is very much part of the material behavior here. The b is also a geometrical constant for our problem because it is just the width of this cross section. Even though we have this horrible looking 7 by 3 power over here, but it is ultimately, this entire term is just a constant because this h is also a geometrical constant in the height of the cross section, which is very much known. So what we have obtained through this integration is basically a connection between this m, the bending moment, and this r, the radius of curvature. Okay, now please note that in this rough, I mean, or just as a side note, I had mentioned that many of you who have had a very strong gate preparation, you'd recall this formula. This mr is equal to ei. Now for our nonlinear behavior, this formula is no longer valid. Rather, what we are obtaining is this kind of an alternative formula. Okay, so please note that this no longer works. Okay, rather we have the alternative version of that for the particular case of the nonlinear behavior given by this sigma is equal to k epsilon to the power 1 by 3, where you note that, so see here for the linear behavior you had basically m is equal to ei divided by r, where this e was the material constant, I was the second moment of inertia, the second moment of area, which included within it just the geometrical parameters, and in the denominator you had this r. Okay, so m is equal to ei by r. That was for the linear behavior. Now if you just try to make or draw an analogy with that, you will see that here also in the numerator we have, just like we had the e there, we have this k here, which is accounting for this material behavior, some kind of a coefficient in the material behavior. This b times h by 2 to the power 7 by 3, that is taking on the responsibility of this second moment of area. This, please note that I am not saying that this is the second moment of area, certainly not. The second moment of area for this cross section is exactly what you have, what you know. Okay, it is still 1 by 12 bh to the power bh cube. So that is not a problem. That is still very much there. But what I'm saying is that just like you had the presence of the I in that linear behavior formula, so also we have the presence of the geometrical parameters in this through these terms. Okay, and just like we have this r in the denominator over here, so also we have this r to the power 1 by 3. Okay, and you note that this 1 by 3 has this connection with this. Okay, so depending on the specific kind of material behavior that we'll be dealing with, we'll have different connections between the m and the radius of curvature. Okay, that is an important lesson to have. All right, so in order to make our steps easier for the subsequent steps that we'll be carrying out, what we'll do is we'll make a direct connection not between m and to this weird looking r to the power 1 by 3. Rather, we'll make this thing simpler in the next page. So I'll just repeat this thing. Let me just copy it. We go to the next page and note that my m is just this thing. Okay. Now, if I am so since I want to simplify the expressions further along, what I will do is I will take this entire combination 6 by 7 kb times h by 2 to the power 7 by 3 and put it inside this single constant c with the r to the power 1 by 3 remaining outside. So what this is going to give me is or I can put a c dash over here, so that finally what I can have is this m cube is equal to c by r. Okay, where you understand that this c is basically is the cube of this c dash. Okay, so this is the thing that we are going to use subsequently. Now, how do we proceed from here? It is just the expression of the m that we have found out. Let us not lose sight of the fact that our interest here is to find out the deflection at the point of application of that force P. Okay, now as I had mentioned earlier, for this nonlinear behavior, we really have to use the complementary energy. Okay, we cannot rely on the strain energy. So, what we'll do is we'll consider this. So it may seem like for apparently no rhyme or reason I'm doing this, but you will get the hang of it in just a minute. Okay, so du dash, so where this u dash is the complementary energy, and we're taking the differential of that. So, and I want to represent it in this fashion. Okay, so this is very much reminiscent of the things that we were doing as part of our proof of the Castigliano's theorem on deflections, except that now we are writing the differential here not in terms of the applied force, rather in terms of the bending moment. Okay, now we have already talked about the corollary to the Castigliano's theorem, and we know that this particular thing we are saying that is the slope. So this is like theta dm. Okay, now again we'll be appealing to our geometrical understanding of the problem, and note that suppose we have a part of the beam like this which has bent like this, and you think that this is some length L. Okay, so when I say length L, I do not mean the capital L which represents the entire span of the beam, rather it is some length L, okay, over which the curvature is not changing, and subsequently we'll specialize this L to a differential element. Okay, but let us not complicate things at one go. Step by step we'll proceed. So the if the curvature of this little portion, uh, okay, is, so if this curvature is r, then you understand that this theta will be given by L by R. Let me write that in yellow. It will be given by L by R. Please note that I am only and only appealing to the geometry here. Okay, so you know that L is equal to R theta, so that's what I'm using here. Okay, now instead of talking about these differentials, uh, perhaps we can write that equal to sign also in yellow. Everything is nice and consistent. So this u dash, can we not write it as in this fashion? Okay, so please note what I have done here is that I've carried out the integrations on both the sides, uh, taking as a limit on the left hand side integration from 0 to u dash. So that's how I get this u dash. And on the right hand side, I'm carrying out this integration from 0 to m. Okay, so uh, what good does this do me? Okay, so all these steps that I'm doing right now, it may seem a little bit arbitrary. Okay, uh, but you will see the benefit of this in just a short while. uh, for now what I'll do is, uh, I will write this, I'll take this L out of the integration. Okay, that doesn't matter, it is like this. And what I will do is, this entire integration that you note is some function of the bending moment, and it is exactly that what I'm going to write this as. So the u dash is like this. Now what is the benefit of actually writing like this? The benefit is that uh, with this understanding that if we have this kind of a formula for a length of the beam over which the radius is not changing, then in order to account for the entire length of the beam, what we can do is we can just carry out an integration, but now considering that this L is actually like a differential element. Okay, so this could have been done in a more formal fashion, but we are proceeding like engineers. Okay, so had we been in a proper maths class, then things would have been done in a slightly different fashion. But uh, those who are more mathematically inclined, I apologize for this lack of rigor and formalism. Okay, but I hope, but the things that we are doing, that is certainly not wrong. Okay, now uh, with this understanding, uh, what can we do regarding the deflection? Because you see, what we have basically managed to do through these rather arbitrary steps is to write an expression for the complementary energy as some function of the m over the integrate over the entire length. So this is the counterpart of what we had written earlier for the strain energy as m square by twice ei dx integrated from 0 to L. That is what we are trying to get at. Okay, so for the case of the linear material for a beam, we had obtained this formula, but please note that because now we are dealing with the nonlinear behavior, we can no longer deal with this. First of all, we had noted that we can not even proceed by the route of the strain energy. We have to do with the complementary energy, but you would still like to make the connection with the bending moment. So that is exactly what we have managed to do here. We have written on the left hand side the complementary energy, but on the right hand side there is an integration over some function of the bending moment, just like we had earlier some function of the bending moment here. Okay, So I'm just trying to draw an analogy here. So now that we have this, can we perhaps hope to find out the deflection, okay, by using the Castigliano's theorem? Let's try to do that. So for deflection, we'll have d del u dash del p. So when I'm writing this, I'm directly utilizing Castigliano's theorem on deflection, uh, where this u dash is definitely the complementary energy. Now, in the previous step, I had obtained this u dash in this fashion, okay, where this f is a function of m, uh, integrate over with respect to x. So this thing can be written like this, and then it can be written like this. Please note again, okay, at every step you should try to draw an analogy with what we had done earlier. So earlier we had this u is equal to m square by twice ei dx integration from 0 to L, and then when we wanted to find out the deflection, what we did was del u del p, and then we found out that to be equal to 0 to L m by ei del m del p dx. Okay, so you see this del m del p business is still very much present in our current formula, but this m by ei that we had obtained very simply, which you note uh, is actually 1 by r, because mr is equal to ei. Many of you know this. Uh, so this thing, the counterpart of that for our nonlinear behavior is this del f del m. Okay, now let's see what is this del f del m. Okay, so uh, so earlier in the previous page we had already said that our fm is basically just uh, this integration 0 to m. This is sorry, right? So does this not give us you think about this for a moment? Okay, so if we have this sort of an integration, does this not imply this? Okay, so probably you can think of going from this side to this side. That will probably clarify your understanding. Okay, now if we have this, then you see that what we had obtained earlier, okay, so that we had this 1 by r del m del p, is it not the same uh, as what we have now? Okay, but the root is quite different. But it is extremely important not to jump to conclusion and say that this thing and this thing is the same. It is certainly not. And why it is not the same thing? You see, although this del f del m may be equal to 1 by r, so indeed we can write this d is equal to uh, 1 by r del m del p, and that probably makes us very happy that okay, we have finally arrived at a form which is very much looking like the previous form. But you see this 1 by r, the connection with the m, that is not so simple. Okay, because we had earlier obtained that m cube but we have earlier obtained m cube is equal to c by r. Okay, if you look back at the previous pages, you'll find that. Okay, or if you just pause the video and maybe go back a few minutes, you'll find that. All right, so And also let us not forget that this c, it is a constant which involves within it various coefficients, uh, like the k, the material behavior constant, as well as the dependence on the width of the cross section and the height of the cross section. Okay, so with these pieces of information, we can go to the next page and actually carry out this integration. Okay. So So you see this, this is 1 by r that we have. So what we need is m cube by c. Okay, so I'm replacing this 1 by r by m cube by c. That's what I've just done here. This 1 by r is m cube by c. So that, and for the beam problem that we have at our hand, because it is symmetric about x equal to L by 2, we have already seen that that symmetry can be exploited to simplify the calculation of this integration. So what we have is this integration from 0 to L by 2, because we understand that whatever is the situation from 0 to L by 2 is exactly the same situation from L to L by 2, moving in the opposite direction. So like this. Furthermore, our expression for m can be written down in terms of the of the reaction forces. So this entire thing can be simplified considerably. So if you just look back at the original diagram, what I'm saying is that if you take a cut section like this, so maybe I just copy this thing. This will be better. So what I'm doing is I'm taking a cut section here, and I'm considering the part of the beam which is to the left of the cross section of this cut section. I'm considering this reaction force, which is, sorry about that, which is P by 2, and I have the bending moment here. This is the shear force, and this expression of the bending moment, this m, this is in the anti-clockwise sense, and the moment contributed by this p by 2 about an axis passing through this end will be equal to p by 2 times x. uh, we write that, and since the sense of that will be in the clockwise sense, there will be a minus, so we have m is equal to p by 2 times x. Okay, so if we substitute that here and carry out our entire calculations, we're going to find out the answer. Okay, so let me not invest any more time on this. uh, I would suggest that uh, whatever we have done here, you please try to repeat this, maybe with a slightly different kind of material behavior, because if you do that, you will see what are the things which we have done as part of this problem uh, which do not change. So uh, there will be certain things like which will be just like an exact replication in every nonlinear problem that you do, but there will be certain things, uh, for example, the connection between the m and the radius of curvature, uh, the specific uh, forms that you end up with, those will be different depending on the kind of material behavior you choose. So if you do a slightly different kind of problem, you will be able to see the things which do remain the same for different nonlinear problems, and the things which do actually change for nonlinear problems. Okay, and that will definitely help you to get a clearer picture, in contrast to the things that we have been discussing compared to the linear behavior. So on that note, I will end this video. Thank you very much.